Welcome to Inorganic Chemistry. Today we are diving into the quantum mechanics of the hydrogen atom. This is the fundamental starting point for understanding how all matter in the universe is built, and it will completely change how you picture atoms. We will move away from old ideas and discover the true wave nature of electrons. Let us start by rethinking the atom. In the past, scientists used the Bohr model, imagining electrons orbiting the nucleus in perfect circle, like planets around the sun. But quantum mechanics tells us a different story. Electrons actually behave like waves. Imagine a hyperactive firefly in a dark jar. You cannot predict its exact path, but you know where it spends most of its time. Similarly, we can only talk about the probability of finding an electron in a certain region. These three-dimensional probability clouds are what we call atomic orbitals. Now that we understand electrons form probability clouds, how do we find their exact shape and energy? We use the time-independent Schrödinger equation. This is the absolute cornerstone of quantum chemistry. It acts as a master formula that governs how quantum systems behave when they are stable and not changing over time. By solving this mathematical puzzle for the hydrogen atom, which has just one proton and one electron, we can discover the exact three-dimensional shapes of its electron clouds. This brings us to the famous equation itself. Conceptually, it asks what specific electron wave shapes remain stable when we measure their total energy. The symbol H hat is the Hamiltonian operator, a set of mathematical instructions. The Greek letter psi is the wave function, describing the shape of the electron wave. E is the total energy of the electron. The formula simply states that if you apply the Hamiltonian's energy extracting operation to the correct wave function, you get back the exact same wave, just multiplied by its total energy. If E increases, the electron is in a more excited state, and the wave shape becomes larger and more complex. To actually use this equation for hydrogen, we need to define what that Hamiltonian operator looks like. In physics, total energy is always the sum of kinetic energy, the energy of motion, and potential energy, the energy of position. For hydrogen, the kinetic part comes from the moving electron. The potential part comes from the electrical attraction between the negative electron and the positive stationary proton at the center. As the electron gets closer to the proton, this attractive potential energy becomes a larger negative number, meaning the atom is more tightly bound. Here is the specific mathematical form of the Hamiltonian for hydrogen. The first fraction represents the kinetic energy of the electron. It includes the reduced Planck's constant, the mass of the electron, and the Laplacian operator, which measures how sharply the wave function curves in space. The second fraction is the attractive potential energy. It includes the elementary charge of the electron, the vacuum permittivity, and R, the straight line distance between the electron and the nucleus. Notice that as the distance R increases, the denominator gets larger, so the attractive energy approaches zero and the bond weakens. Now, looking at that distance variable R leads us to an important mathematical shift. Normally, we locate objects using standard Cartesian coordinates, the familiar x, y, and z axes. But a hydrogen atom is perfectly round, and the attractive force only depends on the straight line distance from the center. Trying to solve the complex mathematics of a round atom using square grid lines is incredibly messy. So quantum chemists switch to spherical polar coordinates. This crucial step allows the massive Schrödinger equation to be broken apart into simpler, solvable pieces. Let us visualize this new coordinate system. Instead of walking along rectangular city blocks, we pinpoint the electron's location using three new values. First, look at the solid line labeled R. This is the direct, straight line distance from the origin, where the nucleus sits, to the point P, where the electron is. Next, we have two angles. The angle theta measures the tilt down from the vertical z-axis. Finally, the angle phi measures the rotation around the xy plane at the bottom. Together, r, theta, and phi perfectly describe any point in a spherical space. With our coordinates switched, mathematicians use a clever trick called the separation of variables. This technique assumes that the total three-dimensional wave function can be split into two completely independent parts that are simply multiplied together. One part only cares about the distance from the nucleus, while the other part only cares about the direction in space. This turns one impossible calculus problem into two manageable problems, a radial equation and an angular equation. Solving these is what magically produces the famous quantum numbers. Here is what that separation looks like mathematically. The total wave function psi is equal to the radial wave function r multiplied by the angular wave function y. The radial function r depends exclusively on the distance r, and it determines the overall size of the orbital. Solving it gives us the principal and orbital angular momentum quantum numbers. The angular function y depends exclusively on the angles theta and phi, and it determines the physical shape of the orbital, like the sphere of an s orbital or the dumbbell of a p orbital. Solving it gives us the magnetic quantum number. Before we move on to the full energy of the atom, let us see this potential energy part in action with a concrete example. We want to calculate the potential energy of an electron in a hydrogen atom when it is located exactly at the Bohr radius. This will show us exactly how strongly the nucleus is pulling on the electron at this specific historic distance. We will extract the potential energy term directly from the Hamiltonian operator we defined earlier. This is the standard Coulomb potential energy formula, taken straight from the second half of our Hamiltonian. V represents the potential energy. The symbol E is the elementary charge of the electron. Epsilon 0 is the vacuum permittivity, which describes how electric fields travel through empty space. And R is the distance from the nucleus. If the distance r decreases, meaning the electron moves closer to the nucleus, the potential energy becomes a larger negative number, indicating a stronger, more stable bond. Let us solve this step by step. We are given the Bohr radius, which is 0.529 times 10 to the power of negative 10 meters. We need to find the potential energy V. We choose the Coulomb potential formula because it perfectly describes the electrical attraction between the proton and electron. We substitute all our known physical constants into the equation, the elementary charge squared on top and 4 times pi times the vacuum permittivity times our specific distance on the bottom. Continuing our calculation, we carefully multiply the constants in the denominator and square the charge in the numerator. Dividing these values gives us our final result. The calculated potential energy is negative 4.36 times 10 to the power of negative 18 joules. That negative sign is incredibly important. It physically means that the electron is bound to the nucleus, trapped in a potential energy well. You would have to supply this exact amount of positive energy to pull the electron completely away to infinity. Now that we have calculated the potential energy at a specific distance, what about the total energy of the entire atom? When the radial part of the Schrödinger equation is fully solved, it yields a master formula for all the allowed energy levels of the hydrogen atom. We are going to use this formula to calculate the total energy of hydrogen in its lowest possible energy state. This is known as the ground state, where the principal quantum number n is exactly equal to 1. This formula comes directly from solving the radial Schrödinger equation. It calculates the total energy for the ground state. The symbol m sub e is the mass of the electron, E is the elementary charge, epsilon 0 is the vacuum permittivity, and H is Planck's constant. The number 1 in the denominator represents our principal quantum number, n squared. Notice that all of these are fundamental constants of nature. This means the energy levels of hydrogen are fixed, quantized values that cannot change. Let us calculate this total ground state energy. We are asked to find the absolute lowest energy state for the hydrogen atom. We plug in all the standard physical constants: the electron mass, the charge to the fourth power, the permittivity squared, and Planck's constant squared. When we compute this massive fraction, it yields a total energy of negative 2.18 times 10 to the power of negative 18 joules. This means the electron is as tightly bound to the nucleus as the laws of physics will allow. While joules are the standard unit of energy, they are very clunky for atomic scale measurements. To make this number more relatable for chemistry problems, we convert it into electron volts. We do this by dividing our joule value by the elementary charge of a single electron. This gives us our final answer, negative 13.6 electron volts. This theoretical result matches real-world experimental data perfectly. It proves that it takes exactly 13.6 electron volts of energy to ionize a hydrogen atom. So, we have proven that the Schrödinger equation accurately describes reality. This brings us to why this matters so much. Understanding the quantum mechanics of hydrogen is the absolute foundation of all modern chemistry and physics. Because hydrogen is the only atom simple enough to solve exactly, we use its mathematical solutions as building blocks to understand every other element on the periodic table. Without this, we would not understand chemical bonds, molecular shapes, or how technologies like MRI machines and semiconductor chips work. Let us review the key takeaways from our journey. First, we replaced the outdated idea of planetary orbits with three-dimensional probability clouds called wave functions. Second, we learned that the Schrödinger equation using the Hamiltonian operator allows us to find the exact energy and shape of these clouds. Third, switching to spherical coordinates lets us separate the math into manageable radial and angular parts. You have now covered the fundamental quantum mechanics of the hydrogen atom, the gateway to all of modern chemistry.